Hi, welcome to Lesson 16D, Inflections and Shape. The goal of today's lesson is to use knowledge of second derivatives to determine the concavity of a function. So here we're given a general curve. This looks like a bit of a cubic. And we see that here we're presented with a local minimum right here, also called a turning point. And here we have a local maximum. Again, there's another turning point where the graph turns. And so let's take a look at, or a couple of seconds to draw a few tangents to the curve here. So I'm going to take a tangent, draw a tangent to right here at the local minimum. And we see there that the tangent to the local minimum, that's where the gradient of the tangent is going to be 0, the horizontal tangent. And so we know that f prime of x at this point is 0. If I were to now draw a tangent, or a couple of tangents to the left of the turning point there, that local minimum, I'd have one like that, and then maybe I have another one that's a little steeper, maybe like this. I won't draw too many of them because it could get confusing if I continue drawing these. And then if I draw a couple tangents to the right of that local minimum, I see we've got a tangent that would be just kind of like this. And then another one further along here, maybe like this. So as you notice, so we've got this first horizontal tangent here right at the minimum point, the local minimum. F prime of x is 0. If we were to estimate the gradients of these other tangents, well, this tangent is very, very negative. Okay, it's very, very steep, it's negative, it's going down to the right. So I could say that maybe, I don't know, as an estimate, maybe that's negative 10. Just guessing. It probably isn't quite that steep, but we'll get the point eventually anyways. So we go down to this next tangent, we see it's not quite as steep as that. It's still negative though. And let's say it's, I don't know, negative 3. It's probably not. Again, just a rough estimate, probably like negative 2 or negative 1.5. Anyways, we move along here. This next tangent is this tangent here. And we see that that gradient is greater than 0. It's now positive. It's going up to the right. So I'll say that that is 2/3. I'll try to be a little bit more realistic with these tangents now. And then the gradient of this next one is a little bit steeper than this one. Let's say that gradient is 1. Okay, so we notice that as the tangents are drawn around this local minimum, we see that they're very, very negative. Like they're negative on the left side, and they're very steep, and they're getting less steep. They get down to 0, and then it's positive. It's not too steep, and then it gets steeper as you go around that tangent, around that curve, that local minimum. Okay, so we see actually that the rate of change of the rate of change, so the way the rate of change is changing, is going from negative to positive. So we can say that the rate of change is actually increasing. It's going from negative to less negative, to 0, to positive, to greater positive. So we can see that the rate of change of the function is the first derivative, so the rate of change is actually the second derivative. We can see that the rate of change going from very steep negative to less steep negative to 0 to positive to steeper positive is actually increasing. So that rate of change is increasing. So that means that the rate of change, the rate of change of the gradient of all these tangents as we go around the curve, the local minimum, is actually greater than 0. We're going to do the same sort of exercise here. If we go to the local maximum and we draw a tangent here, the horizontal tangent, right at the local maximum there, we know that the gradient of the curve at that point is going to be 0. So the gradient of the tangent, that's horizontal tangent, is 0. If I draw a couple tangents to the left of this curve, we see, well, there's one here that's positive. It's not all that steep. And here, if I draw another one a little bit further down the curve, it is steeper. It's still positive. Didn't quite hit it, but get the idea. So this gradient here, let's say that gradient is about 3/2, and this gradient here might be about 1/3, for example. And then, so the gradient is steep-ish positive here. It's still positive, but it's a little bit less steep. Then it goes to 0, and then so we see that the value of the gradient is decreasing as we get from 3/2 to 1/3 to 0. And then we draw another couple tangents on the right side here, and one's not so steep, and then the next one is a little bit steeper, which I'll draw here. And so this gradient, the first gradient here, we know it's now going down to the right, so that's negative. So that gradient, let's say that gradient is negative, what do you say, 4/3 maybe? And then this one is a little bit steeper, so let's say that's -3, just for fun. So around the local maximum, we see that the gradient is positive and steep-ish. It's still positive and less steep. Then it goes to 0. So in between, obviously, if we were to draw all the gradients along for every single point around the local maximum, the gradient would be getting less and less steep as we travel around the curve, and then get to 0, and then we start going down on the other side of the curve, and now we see that the gradients are negative. So we see that the gradients are going from steep positive to less steep positive to 0 to negative to more steep negative. Therefore, the rate of change of those rates of change, being then the second derivative, the rate of change of rate of change, is going from steep positive to less steep positive to 0 to negative to more negative. That means that the rate of change of rate of change is decreasing. Therefore, we see that the second derivative is less than 0. So if we take all this, we can state a few facts about curves and the derivatives and second derivatives. So here, if we say that from judging by what we've drawn here, if f prime of x, so f prime of x being the gradient of the tangent, if that's increasing, as we saw around that local minimum, then f prime of x is concave up. Okay, we see this is concave up. So the rate of change was increasing because it was very negative, very steep negative to less steep negative to 0 to gradual positive to steeper positive. So it went from negative to positive. That meant that the rate of change is increasing. Therefore, the curve itself is concave up. And around the local maximum, we saw that the rate of change was decreasing. Therefore, the curve itself is concave down as we went around that local maximum. So now if we extend this concept, we've been talking about now the second derivative being increasing or greater than 0 or decreasing less than 0. This now brings us to the second derivative test. So if we have some point C, if f double prime of C is greater than 0, so around that point, then we know that the f of x itself, the curve itself, is concave up. and that f of c, the exact point, is a local maximum, sorry, a local minimum, because it's concave up, just like we had here. Again, the other part of the second derivative test, if f double prime of c is less than 0, so around that point, if we were to substitute that point into the second derivative and we get a value that's less than 0 or negative, then the function itself is concave down, so negative and down, then f of c itself is going to be a local maximum. Okay, so positive and up, negative and down are the things that will correlate to each other. And one other thing that we need to take a look at here is that a point of inflection, well, we notice here that between, there's a portion of this curve that's concave up and there's a portion of the curve that's concave down. Somewhere along the line here, somewhere along this curve, the concavity has to change. So here's concave up, here's concave down, and as it turns out, horizontally, halfway between the maximum and the minimum is a point where the concavity actually changes. So horizontally, halfway between those two, there is some x value where the concavity changes, and at that point, that's where f double prime of c is actually 0. Okay, so here f double prime of x is greater than 0 on this part of the curve. Over here, f double prime of x is less than 0 on this part of the curve. So if it's greater than 0 on one side and less than 0 on the other side, that means that somewhere in between has to equal 0. And right here at x equals c, f double prime of c equals 0, and that is what we call a point of inflection. And the point of inflection is the point where the concavity of a curve changes from concave up to concave down, and vice versa, or vice versa. Okay, so where we go from concave up to concave down, or from concave down to concave up, right at that point where the concavity changes is called a point of inflection, and that is where f double prime of c equals 0. Okay, so that's just a little bit about the second derivative test and about concavity and how we use the second derivative. We'll take a look at a few examples tomorrow in order to see how all this kind of fits together. And in the meantime, what I'd like you to do is I'd like you to take a look at, there's a bunch of examples and a bunch of questions that should be perused. So what I'd like you to do is take a look at example 14 on page 403. Then after that, take a quick look at questions 1 and 2 ADF on page 403 to see how this fits together. Then we're going to take a look at example 15 on page 404 before going back to page 403 and, or sorry, I guess it would be 404 now, do questions or take a look at questions 3, B, C, E, H. Then example 16 on page 405, followed by taking a look at exercises 4, 6, 7, and 10 on I guess now page 405. Then look at example 17 on page 407. Then question 1 on page 407, followed by example 18 on page 408. And then finally take a look at what question number 2 asks on page 407. Okay, so all of those things should be taken a look at before the lesson tomorrow, and we'll take a look at some of these examples just to see how the second derivative will fit into your next phase of calculus work. So thanks for watching, and we'll see you in class.